Hello and welcome everyone. I'm Felix, Head of Customer Success, and today we'll do a tutorial of our newest payload, the pulse eddy current. It will be technical, but I'll promise you we'll not do too much theory and we'll head straight into the field. Joao, the floor is yours.
Thank you, Felix. I will be once again your captain for today's flight, and let's look at the pipe we're inspecting. Here we have our demo pipe. As you can see, we have some grinded marks we did, some more deeper defects we have here, and also on this side we have exactly nothing, and this is going to be our point of reference, and with this point of reference we can then detect the defects on this side. And now let's go for the takeoff.
Thank you very much, Joao. I'll guide you now through the flight. And as Joao was already mentioning, we're trying to locate those defects with the pulse eddy current through the insulation. So that's the great advantage of the pulse eddy current, to measure, inspect the pipe without the need to remove the insulation. Important to understand is that the pulse eddy current gives a relative volumetric measurement compared to a reference. So the first measurement or first point Joao is approaching is going to be our reference, and then every point afterwards will be a relative measurement comparing it to the reference. So if we're looking at the inspected view right here now, you can see the graphing tool's two lines, the blue and the red line. Those basically show the decay rate, the signal coming from the pulse eddy current. And those decay rates are compared to another. The red one is the actual measurement, the blue one being the reference. And you can see that the measurement here results in 98%. So the algorithm calculates that, and that's close to nominal, close to 100%. And this is to be inspected, given that on the right side there are no defects on the pipe. And Joao is going to move along the pipe now, taking multiple readings, and then once we come to the left side of the pipe, we expect to get some measurements around 80–75%. Important also to understand is that the pulse eddy current is looking at is taking an average over a certain area. This area is called the footprint, and that also varies with the insulation thickness. So if we are now approaching here the left side, we should be getting, as mentioned, lower volumes. You can see that here we're receiving now 77%, so minor corrosion, quite a significant volume loss. And at those locations, you would usually then follow up, remove the insulation, but specific at those locations, and follow up with wall thickness measurements using a conventional UT probe. All right, let's also talk about the key specification of our pulse eddy current sensor, as well as the limitations. And just important to note here again, Voliro did not reinvent the pulse eddy current technology. This is a third-party sensor company we're working with, and the pulse eddy current technology itself has been on the market for quite a while. The novel thing here is really to have this mounted onto a drone, so you don't need any scaffolding or require rope access to access those hard-to-reach areas. Overall, our pulse eddy current has quite similar limitations to the existing pulse eddy current payloads out there in the industry, but let's just go over those. So in terms of wall thickness, we are limited between 3 and 20 millimeters at the moment, so that's the base wall thickness. And in terms of insulations, we can handle 0 to 100 millimeters or up to 4 inch. In terms of jacketing, at the moment aluminium jacketing is supported. However, stainless steel or galvanized steel is currently not supported. Last but not least, the footprint is basically the area the pulse eddy current is inspecting at the moment. So there is quite a bit of a difference between a conventional UT and a pulse eddy current. Whereas the conventional UT inspects a specific point, the pulse eddy current looks at a bigger area. The footprint for our pulse eddy current is calculated by 50 millimeters plus 0.7 times the liftoff. Best to look that up in our spec sheet. Let's also talk about the general limitations of the pulse eddy current technology. Again, not only applies to our pulse eddy current, but to all pulse eddy current sensors out there. One of them is, it is a screening tool, so it's not the best tool to find pitting type defects, but it's the perfect tool to find those general corrosion under insulation. Furthermore, it cannot discriminate between near side and far side defects. Additionally, the measurement values are usually influenced by metallic structure which is nearby, or also if the metallic structure ends, such as edge effects. However, In that case, trending really helps to reduce the limitations of this. So if you inspect the same asset at the exact same locations year over year, you can really nicely see how those values develop and what the trend is. To conclude, overall, the pulse eddy current technology is a great tool to detect corrosion under insulation without removing the insulation. And then wherever you find your corrosion spot, that's where you will then follow up, remove the insulation and do a conventional UT. And the great novel thing about this one is that you don't need scaffolding or rope access. You mount it onto the drone, fly up there and inspect it straight away. All right, that's it. Thank you very much for listening. And if you do have any questions, please reach out to us. I'm happy to answer all of them. And happy flying, happy inspecting. See you next time.